Hi, and welcome to this video on ratio and root tests in calculus course, where we're looking at specifically these infinite series and trying to determine if they converge or diverge. And I will say that once you learn the ratio test, we'll also learn some other applications for the use of the ratio test later in our power series. But I think you'll find it very user-friendly. One thing to note is that if our ratio is equal to 1, if our ratio test provides a limit, because we're going to be identifying the limit of the next term over the current term as n approaches infinity. So we're looking at that ratio, next term to current term. And if that does not provide any information, that does not mean that it proves anything. It literally means I cannot use the ratio test to determine what this series does. And so I would take a look back and see if there's a different test that we can use. And the same thing is true with the ratio test, with the root test. So as I'm looking at that nth root of the absolute value of that series, so when I have some series to the nth power, the nth root is going to be very convenient for me to take. And if you look at the limit of that as n approaches infinity, I can determine what the series is going to do. So if our limit is, again, this is going to be the absolute value in both cases here, and the square root will be, or the nth root, excuse me, will be the principal root. So an nth power and an nth root will leave a power of 1 behind, so I'll have that absolute value in both. So if my limit is between 0 and 1, so if it's some positive limit less than 1, then I know I converge. If that limit is greater than 1, then that series diverges. And the same thing is true for the root test. If your limit is greater than 1, your series will diverge. If it's less than 1, you converge. And in this case, we do converge absolutely, just like we talked about in that conditional versus absolute convergence video before this. So let's get started so you can see how this works. Now, I'm going to show you which test is helpful in which case here. So if you look at number 1, I would not use the root test. Even though I see I have e to the n squared, n is not raised to the n. So I think this is going to be set up for a ratio test. Ratio test is really good if you have multiple terms, if you have factorials, if you're not quite geometric, not quite p-series, then I kind of default to this ratio test. Whereas number 2 is going to be a perfect candidate for the root test. And it's a perfect candidate for the root test because, as you can see, my whole series sort of pattern 2n plus 3 over 3n plus 2 is raised to that nth power. So me taking the nth root of that is going to be very helpful. So let's just get started so you can see how this works. So for my ratio test, I want to identify, just until we sort of get used to this, what is the a sub n plus 1 term. And in both of these tests, you're using the absolute value, so you don't even have to worry about that alternating condition right now. So that is going to be n plus 1 over e to the n plus 1 quantity squared. Okay? And so what I want to look at now is my limit as n approaches infinity, and I'm going to put absolute value bars. And what the ratio test says is take this a sub n plus 1, so n plus 1 over e to the n plus 1 squared, and divide it by the a sub n that you started with, and evaluate that limit. Again, I've got absolute value bars, so I'm going to come out with something positive, but let's see what it is. Well, instead of dividing by a fraction, most of us will end up going right here right away, where I take that a sub n plus 1 and I multiply by the reciprocal of a sub n. So e to the n squared over n. And so that's what I put in the box for a ratio test. Is most times what's going to be more helpful is if you multiply by the reciprocal, because you're dealing with rational functions typically to begin with. So you'll have a complex fraction. This will help you. Okay, so I'm going to look at what is e to the n plus 1 squared, see if I can maybe algebraically manipulate this at all. So I have n plus 1 times e to the n squared all over e to the n squared plus 2n plus 1 times n. Okay, and when you're multiplying with the same base, you add your exponents. So when I have 3 terms like that in my exponent, this would be the same thing as me saying, I'm going to leave my numerator alone, and this would be the same thing as me saying e to the n squared times e to the 2n plus 1. I could break them out into 3 separate terms, or because I can see eventually these e to the n squareds will divide to 1, I can just leave it like so. It's up to you. All right, so now think about your limit of this as n is approaching infinity. Okay, so as n approaches infinity, I know what the limit is of n plus 1 over n, but I still have this e to the 2n plus 1 down there. So this limit is in fact 0, and as long as that limit is less than 1, I know that this will converge, and I can say it'll absolutely converge because the positive series converges. Again, I kind of took off that alternating condition, if you will, by ratio test. Okay, so let's look at a root test example. So the root test says you're still going to take limit as n approaches infinity, but you're going to take the nth root of the absolute value of your series that you started with. Okay, well, nth root to an nth power, right? That's like saying something to the nth all to the 1 over n, because again, nth root is to the 1 over n. So that leaves all of that quantity to the first. That's why root test is so helpful. And now I'm just evaluating this limit. And we should know this limit from doing it, quite a few times already. If not, you can use L'Hopital's rule or your Calc 1 limit ideas. That limit is 2/3. As long as that limit is less than 1, I know that this series, therefore, converges by the root test. Okay? All right, so let's look at a few more examples. Okay, here's our next example. We have the series that is going from 2 to infinity, and we're going to look at the sum of negative 2n all over n plus 1, all raised to the 5n. And so because I have everything in my series here raised to the 5n, I think this is a great candidate for our root test, because again, the nth root of something to the nth power is going to be very friendly. So what we're going to do is we're going to look at the limit as n approaches infinity of the nth root, and if you choose to write the nth root to the 1 over n power, I think that would be fine as well. Don't forget our absolute value in here. So I have my series, negative 2n over n plus 1, all to the 5n, all in the absolute value underneath that nth root. So we have to be careful, because if n is 2, right, we want to make sure that we're not violating any domain issues here. So, all right, so the nth root of something to the 5n, this should make sense to you that we're going to go ahead and say it's the same thing as limit as n approaches infinity. Keep those absolute value bars, though. It'd be the same thing as negative 2n over n plus 1 to the 5th power. Okay? And limit properties are going to tell us that I can go ahead and just raise that limit to the 5th. And so this limit would be negative 2 to the 5th or negative 32. Again, that's in absolute value bars. So my limit of this whole thing is 32. And since that limit is definitely greater than 1, I would say, therefore, this series will diverge by the root test. Okay? Again, if we get some limit less than 1, we converge. If we get a limit greater than 1, we diverge. If we get a limit that is equal to 1, we're in trouble, and we can't use the ratio test or the root test. Okay? So let's look at the next example. Now this one, even though 5 is being raised to the n, I have that n factorial in the denominator. So the nth root is not going to be friendly because I don't really want to take the nth root of n factorial. I'm not suggesting that the root test only works if you have everything raised to the n, but that's typically what I reserve it for. If I have sort of a hodgepodge of things going on, whether it looks part p series, part geometric, or part factorial, the ratio test usually bails me out and enables me to determine if this is convergent or divergent. So let's go ahead and use ratio test. And until you get a few of these under your belt, if this is my a sub n or my nth term, I think it might be helpful to write out what your n plus 1 term is. So my n plus 1 term is me substituting in n plus 1 in place of n. And then I also think it might be worth your time before you have a limit and you have a big ratio and you have, complex fractions all over the place, or you have a lot to sort of algebraically manipulate, it might be helpful right now just to stop and pause and tell yourself what this is equivalent to. So this is equivalent to 5 to the n times 5 to the first, because again, when you are multiplying with the same base, you add those exponents. So I can break that back apart. And then on the bottom, this is equivalent to n plus 1 times n factorial. Because again, that factorial part means that you're going to multiply by that number and then 1 less than that and then 1 less than that. So it's that product, in this case, this infinite product idea, all the way down to times 3 times 2 times 1. So just keep that in mind because that's going to be what I eventually need here in this limit. So ratio test, so I'm going to perform a limit as n approaches infinity of absolute value bars, and I'm going to do the ratio of this a sub n plus 1. So for now, I'm just going to write it down organically as a sub n plus 1 looks. And then I'm going to say divided by a sub n, but really we know that when we divide by a fraction, we can multiply by that reciprocal. And that just saves me one algebraic manipulation step, I guess. Okay, so I'll say limit as n approaches infinity, and I'm going to write out what I have up there in that gray because it's 5 to the n times 5 to the 1 times n factorial all over. This n plus 1 factorial is really n plus 1 times n factorial, and it's times 5 to the n. So I can write that as one big fraction. And now because everything is factors, I can divide, for example, 5 to the n divided by 5 to the n. I can divide n factorial by n factorial to be 1. Again, I'm doing an algebraic manipulation, not a limit. So now I'll look at the limit. Well, what I have left is limit as n approaches infinity of 5 over n plus 1. That's all that's left. And so if I put infinity in for n, this limit is 0. 0 is definitely less than 1, so I would say this series converges. And you can say absolutely converges by that ratio test. But there was no alternating condition on here, so that might not make sense in that case, but the positive series does converge. Okay, so let's look at another one. Again, this is what I'm talking about when I say part geometric, part p-series, because my numerator here actually looks like that might be the beginnings of a geometric series, and my denominator looks like it's part p-series. Well, you can't take part of one rational function, you can't take part of it and say that part is geometric and that part is p-series unless you're adding or subtracting two series together. So because this is that ratio of them, I'm just going to use the ratio test, and that will help me. So again, I think until you get maybe a few more of these under your belt, you may just want to step aside and say, what is my n plus 1 term? What does that look like? So that would be 3 to the n plus 1 over the quantity n plus 1 cubed. Now, while I don't necessarily want to multiply out that n plus 1 quantity cubed, I will say that I probably need that this is 3 to the n times 3 to the 1. And I'll just keep that in mind as I'm writing this down. So as you identify, all right, what is this limit as n approaches infinity? Again, absolute value bars. Your a sub n plus 1, you can certainly write down what you know you're probably going to need for your a sub n plus 1, which is probably that expanded version, times the reciprocal of my a sub n. And again, that's what I sort of started with, so I'm going to reciprocate that, so times n cubed over 3 to the n. And this is why I sort of like that expanded version better, because this is all really one multiplication problem. And so 3 to the n over 3 to the n is 1. And so I'm left with limit as n approaches infinity of the absolute value 3n cubed over the quantity n plus 1 cubed. And at infinity, I should know how to find this derivative, or excuse me, this limit, whether I use L'Hopital's rule and do their derivatives, the ratio of their derivatives, or if I just look at this from my Calc 1, I should recognize that that limit is 3, which is definitely greater than 1. So I would say, therefore, right, diverges by the ratio test. Okay. All right, so I'm just going to show you a completion of another problem here just because I want to walk you through one part. This is why I might suggest, you know, doing your next term, so to speak, on the side somewhere, is because I can really look at this and say 6 to the n plus 2 is 6 to the n times 6 to the 2. And then n plus 2 is going to stay, but I can say it's 5 to the 2n times 5 cubed. Okay, so I can figure that part out off to the side. Now, one thing about this that people usually miss is that when you substitute in n plus 1 instead of n, you now have 3 places in which to do that. So in my numerator, my denominator, and in my exponent of that 5 in my denominator. And so you've got to be extremely careful when you're doing that with that 2n plus 1. So I showed it right here just so you could get an idea of why there's a common error in here. And that's just because we like to say that it's 5 to the 2n plus 2 or something, because we like to think we're just adding 1. But again, you're substituting in n plus 1 for n. So you do have to distribute that 2, and so that's why it becomes 2n plus 3 as an exponent. And so instead of writing down this step, right, that I just crossed off here, you might go straight to this step right here. If you already have your a sub n plus 1 sort of expanded out, then you can see your factors that will divide to 1 a little bit quicker. So those are just a couple of those common mistakes, but you can take a look or try this problem For yourself, it's a pretty good problem. I'll make it clean so you can write it down or pause the video and try that kind of on your own using the ratio test, and we should get that it will converge by the ratio test. All right, now here is another unique problem that I just want to mention. Doesn't come across all that often, but it is showing you the expanded form of that series. And so it's showing you what each individual term would look like. So this is the form of an infinite product in the numerator and in the denominator, but we have to write the pattern for it. It is not necessarily a factorial because, again, a factorial, if I had 10 factorial, for example, that would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that's not what I have. I only have 2 times 6 times 10 in that numerator. Then I have 2 times 6 times 10 times 14. And so I'm adding one additional factor each term. And so what I look at is the pattern of this, or my a sub n, is going to be 2 times 6 times 10 times dot dot dot. Well, I can see if I just look at these values, 2, 6, and then 10, I'm adding a constant value of 4 every time. So that's how I come out with that 4n portion. And then to get that first term of a 2, I would subtract 2. So if I look here and n is 1, that would be 4 minus 2, or just 2, and so I would stop at the 2 part. And then I do the same thing for the denominator. I see a constant increase of 3. That's how I got 3n. And then I have to add 2 to get that first factor to be a 5. And so then I can look at what is my n plus 1th term. Again, that term is going to have all the same factors that you had before, 2 times 6 times 10 times all the way through that 4n minus 2 factor. But then you're going to have a new factor, the n plus 1 term, if you will, or factor added on to the numerator and denominator. Okay, so you're blowing right through all the old and going on to the next term, which will have one additional factor. So I used my ratio test, and when all is said and done, that ratio turns out to be 4/3. So this will diverge by the ratio test. Most people come up with the fact that that series will diverge, and they do it just by looking at it. And I don't necessarily want you to do that. But they look at it and say, well, obviously this is going to continue to grow. And that's not necessarily true. I don't want you to say things like, well, obviously I'm looking at it and, right? Because sometimes our looks can be deceiving, right? And we can be wrong. There's also many, you can search this if you would like, but there's paradox within mathematics. So there's, for example, you can study the axiom of choice, or there's different paradox that you can study throughout mathematical proof to where things are not as they appear. So I just wanted to show this one just so you could kind of see how it's actually using the test, how it diverges. Okay, and the last one that we'll look at is, again, I don't want you to just see an nth exponent or nth power and think, oh great, I'm going to use the root test, because again, that denominator, I have that factorial there. So any factorial, I just sort of default to the ratio test, but I am going to write what our n plus 1th term is going to look like. So this will be -3 to the n plus 1 over 2 times the quantity n plus 1 plus 1, all factorial. So this will be -3 to the n times -3 to the first, because that'll be helpful for me as I try to algebraically manipulate, my limit here in a minute. And my denominator, that'll become 2n plus 2, so plus the 1 will be 2n plus 3 factorial. And I'm going to go one step further because I'm going to say that this is also I'm going to leave my numerator alone. But in my denominator, the factorial is going to be 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And I go or expand it as much as possible so that I can see that I'm matching something in my initial a sub n, because then I know when I go to look at this as a product, I have a chance of some algebraic manipulation and some division to 1. So I'll show you what I mean here. Limit as n approaches infinity of absolute value, my a sub n plus 1, and I'm going to write that expanded version out because I've helped myself, I believe. So 2n plus 3, 2n plus 2, right? Because the factorial decreases by exactly 1 each time. So I have 10 factorial, remember, is 10 times 9 times 8 times 7 all the way down. And then I'm going to multiply by the reciprocal of my a sub n. So that would be 2n plus 1 factorial over that negative 3 to the n. And then let's do our algebra before we evaluate our limit, because otherwise we will get caught up. If we have an infinite product, I certainly don't want to use L'Hopital's rule because I would just be going on forever. So I'm going to do my division to 1. Negative 3 to the n over negative 3 to the n will divide to 1. 2n plus 1 factorial over 2n plus 1 quantity factorial divides to 1. So I write what I'm left with. Negative 3 is all I have left in the numerator. And my denominator is 2n plus 3 times the quantity 2n plus 2. Again, this is in absolute value bars, but it really isn't going to matter in this case because as n goes to infinity, this limit is 0, which is definitely less than 1. So I would say the series converges by the ratio test. Okay? So you don't have to do this a sub n plus 1, separate. You can certainly do it within the limit. I just think there's a lot going on within that limit. So sometimes having that separated out and just focusing on one thing at a time will make you more successful in your algebra. It's very detail-oriented, but I wouldn't necessarily use the word difficult, but I would say for sure it is detail-oriented, so we have to be careful with that. So I hope you found this video on the use of ratio test and root test helpful. Thanks for watching.